Good morning, everyone. I'm Dean from Anadarko, and 2 years ago, I've come here 2017 to present my real-time dueling solution, and today I come back to present you one of our model in the real-time completion, which actually is a hydrofracture here. So this is a collaboration between me, the second person, and then Yu Chang is my colleague, and also Kay, also from and Louis. We did a great job. And the outline of this is like first I'll give you a high level of what the hydrofracture look like. And then I will show you the real-time completion analysis system. It's just an example similar to what I presented in 2017, the similar architecture. And then Yu Chang will present the three models. Actually, the state start end recognition and ball Pumpdown and SIG recognition. And also, if we may not get time to the third model, but we will just put it here. This is actually hydrofracture. So what we do actually, we drill a well here, and then what we do actually is like look at this side. We will pump the high pressure of the slurry or fluid into the well and then frac the well. So we call this is one stage. This is one stage, this is another stage, this is one stage. And one of our model doing here is try to identify the stage, because this is the base element for any analysis. Without this one, any analysis is worthless. The second model we try to do is like we try to understand when you frac this part, you need to plug this portion so that you can fracture this portion. So we pump a ball. So the ball is like this, all the way down to here, and plug this portion. So we can fracture this portion. Once this is done, then we plug another ball in here and try to. So one of my models is try to identify the ball pump down and the ball sit. Start from the ball sit to the end. That's the hydrofracture, actual hydrofracture. Before, actually, it's not. And that's why it's so important. And we also want to quantify how good job the people do when they pump the ball down from here to here and see. Because some people may take 20 minutes, some people may take 30 minutes. So it depends on the people. So that's why it's important. And I have another colleague, Yu Chang. She did a lot of other advanced analysis based on what we did here. So this is the first analysis we did, but we also have a lot of advanced analysis based on this result. And this is the real-time streaming completion system. What I say is similar to what I presented 2 years ago in the real-time dueling. So here I just changed this to a fragment, and also the victim changed to S233. But the remaining is the same, and all the model is deployed here. This is just an open source example. It doesn't mean Anadarko use this one, but this is a good example. Or any real-time streaming system has a 6 portion. So this is the architecture level. And this is the data you can see. This is the start and end. So actually, what we want is we want to train a model to identify the start and end. So this is one of the model. And another model is the ball seat. You can see that from here all the way to the black line, actually is the ball will pump down and sit here. So we want to identify this event so we can analyze this portion. And so that is more meaningful. So this is let's see. So yeah, you can see here they have a very clear pattern here. That's why we use some of the model from the medical field to identify this one. And the model I use here actually is borrowed idea from the model I use in the real-time dueling side. So actually, some people may claim that my model is overkill, but I don't care. I just want to solve the problem. I don't mind to use a big knife to kill the mosquito, as long as it's kill the mosquito. Okay, Yu Chang, it's your turn.
Okay, thank you, Dean. So I'll continue from this point. So next, I'm going to talk about the first model we developed. It is the stage start and end recognition. So again, here is a time series data of a stage. And in this figure, the red line is the wellhead pressure, and the green line is the slurry rate. And this is the start of the stage when, where the fracturing fluid is starting to be injected into the wellbore. And this is the end of the stage. And our goal is to find out these two labels automatically. So labeling the start and end is very important for quantifying different stage parameters and evaluating the performance of a stage. Traditionally, people manually label this start and end of a stage by sitting in front of a screen, and it could take months or weeks to finish the project. And it also involves human bias in the task and also involves inconsistent performance. So these are the reasons why we are asking the computer to do the job for us. Now, in order for the computer to understand what we need to structure our problem and structure our data. So what we do is we first label the timestamps as zeros and ones corresponding to outside of a stage and inside of a stage. So we can tell when the labels turns from 0 to 1, it is the starting point of a stage. And when it turns from 1 to 0, it's the end of the stage. After that, we use a sliding window to extract the training samples from our time series data. The reason we are doing this is that because when we humans are looking at this problem, we do not isolate every single data point to determine the property of that timestamp. Instead, we are looking at a continuous pieces of time series data to determine the property of the data point of interest. So this is the reason why we're using a sliding window to extract the training samples. And after that, we decided to extend our training features by adding the first derivative and the second derivative of the Slurry rate and wellhead pressure. So this is what our training sample looks like. It is a matrix with 6 rows corresponding to the 6 features and several columns corresponding to the length of the sliding window. And then we label our the training sample using the zeros and ones sample corresponding to the middle timestamp. And this is what our model looks like. It has 2 convolutional layers for higher level features, and then a max pooling, and then a dense layer, and it gives the output. Now, in order to evaluate the performance of our model, we need to come up with some reasonable metric. So the most intuitive metric for this problem is what we call the timestamp-wise accuracy. It is given by the number of total timestamps with correct predictions versus the number of total timestamps. Now, the problem with this metric is that it is actually evaluating the performance on the prediction of single timestamps. It is not a direct indicator of the performance of labeling the start and end. So as an alternative, we come up with another metric, which is what we call the flag-wise accuracy. Here is a simple illustration. Let's say the first row here is the true labels, and the second row are the predicted labels. And we can tell from the labels that this is the true start of the stage, and this is the predicted start of a stage. So what we do is we define a tolerance window centered at the true label, the true flag. And if the predicted flag falls within the tolerance window, then we consider this prediction as correct. So the accuracy will be calculated by the number of correct predicted flags versus the number of the total flags. So this metric is actually directly describing the performance on labeling the start and end. And it also provides an adjustable parameter, which is the length of the tolerance window, to evaluate the performance of the model at different tolerance levels. Next, I'm going to show you some result. So this is the same plot we got, and there is a little blue solid line running across the whole section. And this is actually the true label of the stage. And when it is high up in the sky, it means that this is inside the stage. Let's look at the zoom-in version of this figure. Now, on the left-hand side is the starting part. And we can see that there is a yellow dashed line here, which is our prediction. And it is deviated a little bit from our true label, the true start. But this deviation is still within the tolerance window. So we consider this as a correct prediction. And on the right-hand side is the ending part of the stage. And we can see the yellow dashed line and the blue line overlay very well, which means that this is also a good prediction. And here are some numbers. We can see that when our tolerance window is larger than 10 seconds, we can get an accuracy, a flag-wise accuracy, around 99%. So this is the first model. Next, I'm going to talk about the second model, which is the Bosset event recognition. Well, by that, we are actually talking about recognizing the end of the Bosset event. So on the left-hand side is a figure of the first 5,000 seconds of a stage, which covers the Bosset event. And this red vertical line here is indicating the end of the Bosset event. And our goal is to find out this line automatically. In order to achieve the goal, we come up with a two-step strategy. In the first step, we are going to let the computer tell if there is a Bosset event or not. And this step is achieved by the image segmentation technique. And after that, the second step is to surgically locate the end of the Bosset event by the information provided in the first step, as well as some numerical rules. Now, in the first step, as Ding mentioned, we are using image segmentation to look for this kind of pattern. It's a Z pattern located in the slurry rate. So what we do is we convert this time series plot into an image, and then we overlay a mask indicating the location of the pattern with the converted image. And since the pattern locates only in the slurry rate, we are only including the slurry rate in this converted image for now. So here is one of the examples from the result given by the model. There is an area with lighter color, which is where the computer thinks the pattern locates. And we can see that the edge of this mask is pretty irregular. So we applied some post-processing rule to kind of clean the mask, to clean the edge of the mask and make it, let's say, more convincing. And so if there is a positive area, which is the yellow area here, after the post-processing of the mask given by the computer, if there is a positive area, then we say that there is a Bosset event. The pattern is found in this sample. But sometimes one model is not enough, so we bring in a second opinion from a second model. The second model is actually exactly the same as the first one, except that we are including the wellhead pressure into the training. And with the second model, we are letting these two models vote on the decision on whether there is a Bosset event or not. And if only if these two models agrees that there is one, then we say this sample is positive. And after the first step, the two models says there is one Bosset event in this sample. We apply this set of numerical rules to locate the end of the Bosset event. Now, this set of rules also plays a role in determining if there is a Bosset event or not. So if the two models says there is one in the first step, but the data point that satisfy all these rules cannot be found in this sample, then we revoke the decision from the first step, and we say that there is no Bosset event in this sample. And let me show you some result. This is a confusion matrix from the first step with only one model. And this is a confusion matrix with two models voting. And we can see that the false positive event lower from 8 instances to 3 instances with the presence of the second model. And the F1 score of this of the first step improves from 0.94 to 0.97. And here are some figures of the result. The top figure is the actual end of the Bosset event labeled in this red vertical line here. And the lower figure shows what our proposed strategy thinks the Bosset event locates. And we can see these two lines aligns with each other very well. So this is the second model. And I think we are kind of out of time, so I'll just run through the third part, which is done by Louis. The third part is, after we apply the first two models, we are ready to examine a single stage. And what we are doing is we are trying to segment a single stage as ramp up and constant rate pumping, and then ramp down portion. And we are looking at the second derivative and also the first derivative of the time series data to do this kind of the segmentation. And that's it for the presentation. Thank you.
Thank you to both of our speakers. We have time for one quick question. Take from one over there.
Did you guys investigate a simpler model, maybe just like a rules-based model, before you went to the model you guys chose?
We actually don't have the time to do that because back at that time, this is a pretty time-sensitive project. So as Ting said, we need to get the problem done first. And we actually have something that are similar to this problem, which is RTD downlink recognition. So we kind of borrow the idea from that project and manipulate it a little bit to fit to this project. So I'm sure that, and I'm confident that there is some model that are simpler than what we propose, and it might be more, less resource consuming in terms of computational resource, but we just don't have the time to try it. So yeah.